without the powers of 10. I don't know how she did that.
Well, and you don't need to use them. It's just, it makes my life easier, which is why I encourage, like, it's what makes sense to me is what I'm trying to say.
Oh, so we can just do it, with the old and the new over the old.
Yes, it's just that you'll have to make sure, like, if you don't switch the powers of 10, then you have to expand the numbers out all the way.
Oh, okay.
Or you have to make sure you're putting into your calculator the proper way with the times 10 to the 9th minus something times 10 to the 6th. You know what I'm saying?
Yeah.
That's all.
But yeah, we can wait till after to help me move the 10s.
Okay.
Or when you have time.
Sounds good. Is Brittany there with you?
Yes, she's right here. She's just logging on right now.
Okay, just want to make sure.
Yep.
All right, so what I want to start with is number 10 from from 2F. And so number 10 is a problem where we're looking at if the price had risen appropriately to inflation, what would the price be now? So here's what I'm talking about. So it says, according to a computer performance test, an Apple computer that cost $1,000 in 2012 had computing power greater than that of the supercomputer that sold for $30 million in 1985. If computer prices had risen with inflation, how much would the 1985 supercomputer have cost in 2012? So this is some odd phrasing of this question, but what they want you to think about is that in 2012, you could buy a computer for $1,000, right? It was way more powerful than what they considered the supercomputer in 1985 to be able to. I mean, my cell phone now has more computing power than the laptop I bought when I went to college in 2001. Like, it's crazy to think that like this little thing is like 10 times more powerful than my first laptop. So if we want to adjust this cost for inflation, we would think that we're looking at CPI in 2012 over CPI in 1985 equals the money in 2012 over the money in 1985. Now, yes, I know they gave us a price of $1,000 in 2012, but we're not using that price because that price was not appropriate to what the inflation has changed. Instead, we're going to use the price in 1985 of 30 million to come up with what it would have cost if prices for computers had just increased due to inflation versus what they've actually done is gone down with the computing, even though our computing power has gotten higher. So we're going to need to pull our CPIs from the very first page of our notebook for this section. So we're going to bear with me while I swipe back a few pages. So the CPI in 1985 was 107.6, and the CPI in 2012 was 229.6. So we're going to use those two values at the end. Okay. So the CPI in 2012 was 229.6. The CPI in 1985 was 107.6. Now we don't know what the cost would have been in 2012 if the computer had stayed, the price had continued to rise with inflation. Okay, we know that in real life it cost $1,000, but if our price had continued to increase with inflation, what would it have been? In 1985, it was 30 million. So in order to solve for X, we're going to use cross multiplication and division. So I want you to solve for X and send me your answer in a direct message. When you're entering your answer, if you could add apostrophes, or not, sorry, not apostrophes, commas as you're entering the number, so it makes it easier to read in between the digits, that would be awesome. Okay, so if we do cross multiplication and division, we come up with a price of $64,014,869.89. So if the price of the computer had stayed with inflation, meaning just increased at the rate of inflation, this is an insane amount of money, right? Thank God. Our electronics have not risen with inflation. They've gotten cheaper and yet more powerful. But so not everything goes up with inflation. Most things go up faster than inflation, but thankfully electronics, those types of things have gone down. So any questions about that before I switch gears?
My hardest part of this whole section is just taking a word problem and making it into a formula. Once I've got the formula, I'm good. I've never been good with word problems, but I've been struggling with this whole section, which is why I'll meet with you after class. So
sounds good.
One of the hardest parts.
That is, yeah, I think you are not alone at all, Don. Everybody feels that way. And of course, me sitting and breaking it down for you, you're like, oh, okay, great. And then you go and look at it on your own. You're like, nah, I don't understand what we're talking about here, right? But the more that we do, the easier it gets. Okay, so chapter 3, let me give a preface about this. Chapter 3 is all about probability. And you will need this section when you go on to Math 105, Math 140, and Math 115. All three of those classes will build on Unit 3, okay? So it's not like I'm teaching you this for no reason. There's a reason why we cover this, so that you have the building blocks so that when you go on to those other classes, you can get into more complex probability. In order to talk about probability, we first need to talk about understanding the idea of a set and subsets of numbers. And so 3A kind of feels like it comes out of left field, but it does have a purpose. So when we look at 3A, to begin with, it seems like we've got this crazy set of vocabulary at the beginning, okay? So I'm going to go through parts of it and then I'll come back to it, okay? So first of all, the first definition we're looking at is the definition of a set. And a set is considered a well-defined collection of objects. And so the well-defined part is important. So if I were to say the set of all Math 94 students. Oh, Kaylee, thanks for letting me know. I will get those notebook pages uploaded right now. I'm sorry about that.
Thank you. Okay, I have mine right here, but
Okay. I didn't realize that wasn't in there. That is good to know. I'll get that updated after class. So if I were to say all Math 94 students, well, that is a very broad definition. That could be all students who have ever taken Math 94. It could be all students who are currently taking Math 94. I could mean it in my brain to be all of my Math 94 students because I teach 2 sections of this class. It's a broad definition, but I could say all students enrolled in Math 94 section 2/60 in fall of 2022, and that is everybody that is sitting in the Zoom class. That is a well-defined because it gives the parameters. We know exactly what we're talking about. And so that's what we mean by well-defined. Objects or elements are members of a set. So this notation right here, this looks like an E, is the notation for element. The same with if you take that E and you draw a line through it, that is considered not an element. It negates it, okay? And the elements are usually denoted by lowercase letters, A, B, C, while the sets themselves are usually denoted by uppercase letters. The elements of a set can be displayed by listing all of them between braces. And so, or curly brackets, the other thing that those are called. And you will notice the more I write these, the more they just start to look like squiggles, but we all do our best, right? They're not the easiest thing to draw, but again, we just do our best. The notation A, B, C, and then the triple dot Z is referred to as roster notation. The reason it's roster notation is because they are being listed in alphabetical order. And we can also use what we refer to as set builder notation to avoid listing every element of the set. So this set here, A, B, C, dot, 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 Z, is all the letters in our alphabet, is what that's trying to indicate. However, if I write it out, we can use set builder notation to describe set B as B is equal to the set of elements X, such that X is a letter of the English alphabet. This vertical line here means such that. Now, you are not going to be writing these out. Okay, I don't want you to think, oh my God, Erin, what are you suddenly having us? But you will be reading them. And so I want you to understand if you're choosing an answer, what it's saying, okay? And so again, this notation right here says B is the set of elements X. So X is a generic variable there because it's referring to any element that could be in it, such that X is a letter of the English alphabet. So I'm going to pause us there and we're going to look down at our first examples. So we're going to answer the questions below considering sets A, B, and C. So we have set A, which is the numbers 1 through 5, set B, which is the numbers 4, 6, and 8, and set C, which is the numbers 3 and 5. And then we have this set U. The U is called the universal set. And the reason it's called universal set is because A, B, and C are all subsets of U. And I'll come back to the definition of subset. I just want you to understand what those are saying. So number 1 says the set builder notation X, such that X is an even whole number between 3 and 9, applies to which set? Does it apply to set A, set B, or set C? That definition. So again, the notation that X, such that X is an even whole number between 3 and 9, does it apply to set A, set B, or set C?
Set B.
Yeah. Because we even numbers between 3 and 9. So the first even number between 3 and 9 is going to be 4, and the next one's going to be 6, and then the last one's going to be 8. So that is a verbal description of set B, because B is equal to 4, 6, and 8. Kaylee.
So when would we, what would be the reason for us using grouping like this, I guess is what I'm wondering.
So right now, we're familiarizing ourselves with it.
Okay.
3B, we're going to start looking at how sets interact with each other.
Mhm.
And then 3C and 3D, we're looking at probability. And so we use these descriptions in order to define groups that we're working with or sets that we're working with to find the probability of those.
Okay, so we're like sorting data and information with these.
Sort of,
And-
yeah. We're giving you an introductory to mathematical notation as it pertains to sets,
Uh-huh.
because after this class, you're going to need that information.
Okay, sorry,
you're
I just
gonna
kind of have to
build
know
upon
like the whole picture so I can see what part we're working on. Otherwise, I don't understand it.
Yeah. At first, it feels a little weird, but it'll get easier, I promise.
Okay, thank you.
So number 2 says, give a set builder notation definition for set A. So A is the set 0, 1, 2, 3, 4, 5. So how can we describe that? Like just in normal words, don't even worry about using the notation. Just tell me, how could I describe those numbers?
This is the beginning of the counting numbers.
I think it would be any whole number from 0 to 5.
Okay, so we've got our whole numbers from 0 to 5 inclusively, because we want to include those two, right?
But 0 isn't a whole number, is it?
It is still a whole number.
Oh, okay, I wasn't sure if it was part of the whole numbers. I gotta go look at my notes.
So
Or if
it's
it was part of
not, oh man, is it not a natural number?
That's what I was wondering. Let me look real quick. I have it all written down right here.
Yeah.
Because those confuse me, so I just have a whole chart.
We could also, if we're worried about having the difference between whole number versus natural number, it's still an integer, right? They're integers from 0 to 5 inclusively. So we can say that A is the set of elements X such that X is an integer or a whole number greater than or equal to 0, but less than or equal to 5. Using the equal part underneath that is the inclusivity, meaning it's going to include from 0 to 5.
So 0 is a whole number and natural numbers are counting numbers starting at 1.
Yeah, that's what I thought. Okay, so in order to be able to answer the next set of problems, which is 3 through 10 on the next page, we need to go through some of the rest of the definitions. I'm gonna pop up here. So the next piece we have N of A. And this is the notation that indicates the number of elements in a finite set. So when we think about the number of elements, that is the number of objects. So if I were looking at, say, set B, the number of elements in set B, there's 3 numbers in set B. So there would be 3 elements in set B. The empty set is the set with no elements, and this set is a subset of all sets. The notation includes writing out null set, 0 with a line through it, or empty brackets. Do not write that. Don't write a 0 with a line through it inside the brackets. That is jargon. That's not proper notation. So the null set is either the 0 with a line through it or completely empty brackets. Those are the 2 ways that you would represent it, okay? We talked about the universal set, but again, the definition for the universal set, which is a capital U, and they put these little lines on the top. It's the set containing all elements, set containing the elements of all the sets under discussion. So like in our examples, we're talking about sets A, B, and C. All of their elements are listed in that universal set. So the universal set would be like the overarching thing that these little pieces are in. And then we have the idea of a subset. Set A is a subset of set B, denoted, and you'll notice what am I trying to say? What is this thing called? The notation for subset is like a sideways U with a line under it. And it's set A is a subset of set B if every element of A is also an element of B. It can also be where if every element of A is also an element of B and they're equal to each other, they're still considered subsets. So we've got this line underneath that means that it's basically less than set B or equal to B. So it's got everything in B or maybe a little bit less than what's in B, but still everything in A has to be in B. If you draw a line through it, it means that it's not a subset. And then we have this idea of a proper subset. Set A is more specifically a proper subset of B if all the elements of A are also elements of B, but A does not equal B, therefore A is a proper subset of B. Again, this also means that A cannot equal B, so there are elements in B that are not in A. And if we put a line through it, that means that it's not a proper subset. Then we have the idea of set equality. 2 sets, A and B, are equal, written A equals B, if and only if they have exactly the same elements. And then the last idea is the complement of a set. And the complement of set A, and it's written with an apostrophe after it, is the set of all elements which are in the universal set, but not found in A. Another way you'll see complement written is A with a little tiny C at the top. You'll more commonly see that in Math 140 and Math 115, if those are the classes you're going to after that. After this, I just want you to know that that's what that notation means. It means complement. So we're going to use these definitions now on the next page. So I'm going to turn to the next page and I'm going to rewrite our sets at the top. So we've got A, which is 0, 1, 2, 3, 4, and 5. B, which is 4, 6, and 8. C, which is 3 and 5. And then we've got our universal, which is 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So number 3 says, what is the value N of C? So remember, N of C means how many elements are there in set C? Well, C is equal to 3 and 5. So there are 2 elements. Because there are 2 numbers in it, there are 2 elements. So the N of C is equal to 2. So we look at number 5. We have this notation here, 0 sideways E A. Again, what is this asking? This question says, is 0 an element of set A? That's what that notation means. Well, if we look at A is equal to the set that contains 0, 1, 2, 3, 4, and 5. And 0 is right there. So the answer to this is yes. The second part says, is 0 an element of B? Well, B is equal to 4, 6, and 8. So do we see 0 listed in that list? No. So again, because 0 is not in that list of elements, it's not an element of B. So is 0 an element of B? No. All right, we're going to go over to the right. It says, is C a proper subset of A? This notation, what is this saying? Is C a proper subset of A? Well, in order for something to be a proper subset of another, everything in C must be in A. So, in order for C to be a proper subset of A, everything in C must be in A. So if we look at A, there's A, and there's C. Is everything in C and A? Yeah, C is 3 and 5. which is clearly in the list of from 0 to 5, right? So is C a proper subset of A? Yes. But we can't go the other direction. The second question says, is A a proper subset of C? Well, A is bigger than C. So clearly A is not a subset of C. So they don't go both directions. Because I can't fit everything in A in set C, because A has, 6 elements and C only has 2 elements. So clearly A is not a proper subset of C. Okay. Number 6 says name all the possible proper subsets of B. In order to name subsets, they must be in the curly brackets, okay? So set B. Hold on, you guys, I'll be right back. Oh my gosh, I'm so sorry. My cats were screaming like one of them was dying, and I was like, oh God, what is happening? All right, so B is equal to 4, 6, and 8. So to list the proper subsets, we're going to list all the possible combinations of those letters that are in there. Not the letters, the numbers, excuse me. So the first proper subset that you will always list is the null set. And remember, the null set has nothing in it, because the null set is always a proper subset or a subset of a set. After this, I like to list all the single element subsets. So that's going to be 4, 6, and again, my brackets get real gross real fast. These are not easy to draw, and 8. So I've got the set of no elements, and then I have each of the single element sets. And then after that, I want to do all the 2 element sets. So I can have 4 with 6, or I can have 4 with 8. And what's the last combination?
6 with 8.
6 and 8, right? So just so you know, I want you to think about sets as being like a bag. If I wrote the set 8, 6, that's the exact same thing as the set 6, 8. Order does not matter within it. If I took those 2 numbers and I drop them in a bag and I shake it up, it's still the same combination, right? So the order doesn't matter. It's not going to make it a new set if you swap the numbers, okay? Because we want only the proper subsets, we can't include the set itself. Now, something I want to drive home. Okay. So remember in number 3, it says, what is the value of n of C? That is the number of elements in C. You do not want to list those in brackets. The only time you're listing numbers in brackets is when you're actually listing subsets, okay? So make sure that you're not swapping your notation, okay? Or if it says, what are the elements of B? Let's say I wanted the elements of B. Or we would just list 4, 6, and 8. We do not want to put them in brackets because that is then saying we're talking about a set, and I don't care about the set. I'm just saying, what are the individual elements, okay? So when you include brackets, you're now creating a set. And if I just want to know the elements, you're not going to include those. All right,
So-
number 7 says, is A not a proper subset of B a true statement? Is A not a proper subset of B a true statement? So what do we think?
No, because it has elements that don't fit into the set of B.
Right, so A's got 6 elements in it, right? B's only got 3 elements. So we can't fit 6 elements in 3 elements, first of all, just from a pure like number standpoint of how many objects are there. The other problem is that there's stuff in A that's not in B. So in order for something to be a subset, everything in the subset has to be in the bigger set. So A is not a proper subset of B is a true statement. And yes, because it's not. Kaylee.
So my question is, if the elements in A were decimal points between the numbers of B, does that make sense what I'm saying? So if it was like 4.5, 5.5, anything in between 4 and 8, would it be a subset of B? Even though there's 6
No.
numbers?
No,
Okay.
because it's saying you have to look at the exact values.
Okay, so even if they were decimals, they wouldn't fit in because B doesn't have any
Those
decimals.
exact values.
Okay, okay.
Yeah. So number 8 says, is the null set a proper subset of C a true statement? What are we thinking? What did I say about null sets?
I don't remember what you said about null sets.
That's okay. Think about what I listed in number 6. If you look above, what did I list in number 6? So in number 6, we had to list all the proper subsets, right? And the very first set that I listed was this guy.
It's the null set, so it would be.
Right, exactly. So every set contains the null set as a proper subset. Therefore, is the null set, so remember null set is the same as 0 with a line through it, which is the same as empty brackets. Those look like. There we go. So every single set contains the null set as a proper subset. Therefore, is the null set as a proper subset of set C a true statement? Yes, because every set contains the null set as a proper subset.
Would
What
there
is the
ever
point?
be a
Oh.
null set that didn't have that? Or-
So many. Melissa, you start and then Kaylee.
I said, would there ever be a null set that wasn't a proper subset?
No.
What is the point of a null set?
So the null set is the absence of the things. So you will end up finding the probability of the null set, which is the absence of that happening, okay? And so the next piece is talking about the complements of a set, okay? So number 9 says, which elements are found in C complement? So C complement is not C, but still in the universal. So if we look at our universal, 0, 1, 2, 3, 4, 5, 6, 7, 8. And we take away C, and C is the set of 3 and 5. Therefore, this null set of, or excuse me, not the null set, the complement of C is the set of numbers 0, 1, 2, 4, 6, 7, and 8. Therefore, if we list the elements, we then list them outside of the bracket. So the elements are 0, 1, 2, 4, 6, 7, and 8. So again, Kaylee, to answer your question, why do we care about the null set? Because we have to know that something not happening is always a possibility. So the absence of something is always a possibility. So our last one, number 10 says, is 5 not an element of B complement a true statement? Since we're running out of room, I'm going to put this one on a separate sheet of paper so that we can talk about it. So bear with me for a minute while we go and get a second sheet of paper. So it says, is 5 not an element of B complement a true statement? So in order to answer this, we want to first find B complement. So remember, B complement is everything in the universal that is not in B. So B is a set of 4, 6, and 8. The universal is a set of 0, 1, 2, 3, 4, 5, 6, 7, and 8. Again, we can see that B is a subset of the universal because these are the elements of B. Right? It fits within there. So if I get rid of those elements, what I have left is the complement of B. Therefore, B complement is going to be 0, 1, 2, 3, 5, and 7. Because that's everything that's left in the universal once I take B away. So what can you tell me about the number 5 in B complement? Is the number 5 listed?
5 is not in the set of B.
And not in the set of B, but is it listed in the set of B complement?
Yes,
Yeah, in the blue set, do we see the number 5? Yeah, so B complement contains 5. Five is an element of B complement. So 5 not being an element of B complement is a false statement. So a lot of what we're doing in Unit 3 has to do with logic and reasoning. And so when you're working through these, I want you to go back to what the beginning part is, meaning in order for us to even know if this is a true statement, we need to identify what B is, and then we have to define what B is not, meaning the complement of B. And once we have those two, then we can go back and read the question and decide, is it a true statement or a false statement based upon what we found. So with sets, we can perform operations. And so we have the idea of the intersection of two sets. And when we think about the intersection, I want you to think where two sets overlap, because it's what they have in common. So the intersection of two sets, written A intersect B, and the upside down U means intersect, is the set
He's still there?
I think we lost her.
Okay, I was gonna say, is it just us?
No, I can't see her here either. She's gone.
She'll be
He's
back.
gone.
Hey, better her than me.
Are you guys like completely understanding this?
No, I'm actually pretty far behind right now with being sick and being out of class.
I'm just
Yeah.
kind of like listening. I think I'm gonna have to rewatch this lecture.
Same here, Kaylee.
I feel like I have to rewatch all the lectures. It's almost easier to just go back when you can pause her to read.
Exactly. Agreed. She moves very fast.
You know, though, if you go into the videos, those seem more helpful for me, like when I'm taking notes and stuff, because she does a lot of the same thing, but it's not like an hour long.
Yeah, but I thought this was gonna be easier than the last stuff, but we'll see.
Well, I think it's going to get harder because we're actually moving into probability now, and the last stuff was just a review.
Thanks, Kaylee.
Ugh. We might have to like get together and study if any of you want to. I would be down for that.
I agree. Just finding the time with chemistry and this together.
Chemistry was like so time consuming.
Oh, she's back. I see Erin. She's
I'm
back.
back. We had gone so long without the internet dying on us. I keep complaining to my internet company because they're still supposed to put in like the permanent fiber, and it was supposed to be done 2 months ago when we moved in, and it's not done, and they're kind of tired of hearing from me, but I don't stop complaining because we need proper internet.
I went with Starlink out here in Libby.
Did you really? How do you like it?
As far as like streaming TV and being online here at school, it's great.
Mm-hmm.
I think that's what we use for search and rescue too. They gave us like a router to take with us when we go on long searches because it reaches so far. We can use it up in the mountains.
That's crazy.
Yeah, they definitely have a lot of different options, especially for being mobile like that.
Yeah, we have weird, like, it's considered cellular internet because it's basically like, you know how you can use your phone as like a hotspot or whatever? It's like that, but like on a higher scale, but every once in a while it decides to die. Anyways, let's get back to what we are doing. So, we were talking about set operations. So, we can have the intersection, which is where they have to be common to both, or we can have the union. And when you think of the union, think of like taking two sets and putting them in a bag together. So it's like everything together between the two. Okay. And so the definition is that A union B is a set of all elements in A or in B. So again, you could think of this as combining two sets together to create a larger set that contains both A and B. And then we have the last idea of disjoint sets. And these are sets which have no elements in common. A and B are considered disjoint if and only if their intersection is the null set. So if we think about sets that have nothing in common, think of that don't overlap, cats and dogs are disjoint sets because there are no catogs. There are no animals that are considered both cats and dogs, right? Where lions and tigers, they have bred those together and made a liger. Therefore, lions and tigers are not considered disjoint because they overlap at the ligers. Which is a crazy idea, but it's a true thing. They really did do that. So how are we going to do this with numbers? So we've got our three sets. These are three new sets. We've got set A, set B, and set C, and they're all subsets of our universal set. So before we get into A or to 1 and 2, I want us to look at this universal set. Universal set is 0, 1, 2, 3, 4, 5, 6, 7, and 8. And let's identify the three individual sets. So I'm going to use a highlighter in 3 different colors. So the first one I'm going to do is I'm going to highlight all of set A. So that yellow is set A. Okay. And then I'm going to do set B, which is 4, 5, 6, and 8. So I've got 4, 5, 6, and 8. Those are set B. And the last set is set C, which is 3, 5, and 7. So when we think about intersections, I want you to think about colors overlapping. Okay. And when we think about unions, we think of just anything that's colored. So A and B, if I want to union them together, the union of A and B is all numbers shaded yellow or blue. So if I look at my universal set and I look at all the numbers that are shaded yellow or blue, well, the yellow ones are 0, 1, 2, 3, 4, and 5. Now, number 4 is both yellow and blue, right? But we've already listed it, so we don't need to list it again. The number 5 also shaded yellow and blue. Since we've already listed it for the yellow numbers, we don't need to list it again. But we still have a couple of numbers that we haven't listed yet that are also shaded blue. So we need to add the number 6 to our list and the number 8. And that is the set of A union B. Because those are all the numbers that are shaded either yellow or blue. But then number 2, it says A intersect B. So again, this is A union B. And this is A intersect B. And for this one, we want all the numbers shaded yellow and blue. So they have to have both yellow and blue in order to get here.
So when you're putting them in a union, you're just joining the two sets.
yes,
And when you're, what is the second one?
intersecting them,
Okay, so then you're just taking the numbers that overlap from the sets.
correct.
Okay,
So that's why I like to use the color, because we can see where are those colors overlapping, right? So we can see that yellow and blue overlap at 4, and yellow and blue overlap at 5. If we wanted to list what does A intersect B intersect C? Is there one number that is both yellow, blue, and pink? Yeah,
5.
number 5.
5.
So 5 would be the intersection of A, B, and C, because that is the number that is yellow, blue, and pink. Okay, let me copy my little thing so that we can take it to the next page with us. So that's this is how all of our sets overlap. We write our sets individually. Actually, let's take this guy. Hey. Oh, you. Oh. There we go. Okay, so remember A is 0, 1, 2, 3, 4, and 5. B is 4, 5, 6, and 8. And C is 3, 5, and 7. Okay. Just keep those in mind as we look at number 3. So number 3 says A complement union B. So A complement union B means the union of not A and B. So first, we need to find a complement. So if we look at our universal set is 0, 1, 2, 3, 4, 5, 6, 7, and 8. And A is the numbers from 0 to 5. So if we take away the numbers 0 to 5, we're left with 6, 7, and 8. Therefore, A complement is equal to 6, 7, and 8. Because it's not A. Again, these numbers were A. And therefore, these are not A. So because we want to union it with B, that means we're taking everything that's not A and B, and we're just putting them together. So A complement union B. If I start by listing B, I've got 4, 5. The number 6 is common to both of those. B would have 8 be part of it, as is not A, but we have to make sure we list 7 because that is in the not A, and then B. So again, we're just taking those sets and we're joining them together. So questions about 3 before I move forward?
Where do we get the 7 from? Because I don't
This-
see it in B.
But it's in the not A part.
We're comparing it into the universal.
So we had to identify what was not A, which we took out of the universal, right? So not A is 6, 7, and 8. B is 4, 5, 6, and 8, and we're joining those together, meaning we're smushing them into one set together.
So that's what the complement is the numbers that are not in the set, but are in the
Correct.
universal set?
Yes.
Okay.
So we're going to look at that again in number 4. So number 4 says not A intersecting not B. So we're saying, where does A complement intersect B complement? So first, find A complement. Second, find B complement. And then third, find where they intersect. So A complement, we already know for number 3, right? We found that. A complement is 6, 7, and 8, right? So part 2 says find B complement. So remember, B complement is everything that's in the universal, but not in B. So if I take my universal, and remember B is the numbers 4, 5, 6, and 8. So we go to that universal and we cross out 4, 5, 6, and 8. What is left listed there? Well, what's left, everything that's left in this set that I have not crossed out is what is in B complement. So I've got 0, 1, 2, 3. Again, I can't list 4 or 5 or 6 because those were all in B to begin with. I can list the number 7, but I can't list the number 8. So the third step says find the intersection. So if I have A complement is equal to 6, 7, and 8, and B complement is equal to 0, 1, 2, 3, 7. Is there a number that is in both of those?
7.
Yeah. So because the number 7 is listed in A complement and in B complement, A complement intersects B complement at 7. Because that's the number that is listed in both of those. That's where they would overlap.
So are the complements part of like preparing, like you said, for possibilities that haven't happened?
It's the opposite of an event.
Okay.
Yeah. So we have to consider complements because they would be the opposite of something happening. Okay. We have 2 more. I want to do 5 because that has the multi-step. So when you're looking at number 5, we've got a set of parentheses, right? So that means do that part first. So we have A union B, and then we're looking at intersecting C. So first, we want to find A union B. So remember, when we're unioning 2 sets together, we're just combining them. So if I have set A, which is the numbers from 0 to 5, and set B, which is 4, 6, and 8, if I join those 2 sets together, I've got 0, 1, 2, 3, 4, and 5. So that's all of set A. And I go over to the set B, I've already listed the 4 and 5 by listing out set A, right? You don't need to list them a second time. So when I'm adding B in, the only pieces that are missing are 6 and 8. So again, unions, think about labor unions. They're a big group of people. When you union sets together, they get bigger, the final set, okay? So now if we look at set C is 3, 5, and 7. So the question is, where does A union B intersect C? So looking at these 2 sets that I've listed here, we've got A union B in green, set C listed in blue. Where do those intersect?
3 and 5.
Yeah. So because the numbers 3 and 5 are listed in both, that is where they consider to overlap or intersect. And therefore, A union B intersects C at 3 and 5. Okay, we did a lot today. I want you to try number 6 on your own, and we will start lecture with that on Tuesday. Okay, try number 6 on your own. It says C intersect B, and then outside it has the complement. So your first step here is going to be find C intersect B. And the second step is going to be to find the complement of C intersect B. So
Thanks,
again, I
Amy.
want you to try number 6 on your own, and that's what I'll start lecture with on Tuesday.
Do you want our answers now?
No,
When are we gonna know the grade for our quiz?
probably on Friday. You got to give me a little time, Melissa. You just took it yesterday.
I'm nervous.
Don't worry about it. I'm sure it went just fine.
I definitely struggle in the quizzes to like, not necessarily quizzes, but that specific lesson. It's hard for me to figure out what I'm trying to, what the end ratio is, and then make all the little ratios leading up to it. Once
Yeah.
I figure all of that out, it's like a lot of trial and error. That the next part's easy, but it's just figuring out, working backwards almost is
Exactly.
I'll have to
And
do it.
it's always a good, think about where you want to end and look at where you're starting and think, okay, well, if I need to get to this, what are the units of measure I got to cancel in order to get to that? And then you can start to work your way backwards.
yeah, it's definitely like a mind workout.
All right, everyone. I'm going to let those of you who want to go. I hope you have a good weekend, and I will talk to you all next week. Okay.
Thank you.
Bye.
Yeah, well, I'm gonna stay.